In this video, we will look at another service provided by the data link layer, that of reliable data transfer. But first, a quiz. Where are we placed right now? We saw that the role of the data link layer is frame by frame next hop delivery. And when frames get passed over a link, they can get corrupted. At times, they can even get lost. And we saw that error detection is a mechanism that can help detect corrupted frames. Error correction can also help, but in some cases, when there are too many errors, there is not much that can be done. So what do you do next once that you have detected that your frame is bad or you didn't even receive a frame, where frame is lost? Naturally, when frames are corrupted or lost, a lot of applications don't like it. So you want to provide a reliable data transfer. So the job of this reliable data transfer protocol is to recover from these corrupted or lost frames. And this is one of the most researched problems in networking. Reliability as such is handled both at the link layer as well as the transport layer. Providing reliability at link layer is a lot simpler than that at transport layer. So at link layer, we will develop the framework for providing reliable data transfer and we will extend it as part of the transport layer. So here is the outline for this video. In this video, we will develop a reliable data transfer protocol. So this protocol provides a reliable channel service to the higher layers. So as far as the higher layers are concerned, they send the data and to them it looks as if they are sending the data over a reliable channel. So they don't have to do anything about it. But in implementation, what happens is they are sending the data which is being handled by this reliable data transfer protocol, which is in turn operating over an unreliable channel, but it is giving an impression of a reliable channel to the higher layer while it is operating over an unreliable channel. So what we will do here is we will start out with an unreliable channel with bit errors only and then slowly add losses on top of it, and we will incrementally build the reliable data transfer protocol. So first we will look at a channel with bit errors. What this means is the packet can get corrupted but not lost. In other words, you will receive the packet, but it can have some bit errors as part of it. We saw that we need some functionality. So what we are going to do here is list the functionality that is needed to provide reliable data transfer. So one functionality we will definitely need is error detection mechanism to determine whether the frame or packet is corrupted or not. This we have seen is achieved through checksum CRC and so on and so forth. What else do we need to provide reliable data transfer? So let me take the telephone analogy. Suppose you're talking over a noisy telephone line with someone. How do you ensure as a speaker that whatever you speak is actually being received by the other user? That is, how do you ensure reliability over a noisy telephone line? What human protocol do you use? So basically, the receiver is going to provide you feedback. And there are two types of feedback. Positive feedback. So basically, the receiver says, aha, oho, acha, okay, This is positive feedback in the form of ak. There is also negative feedback. In other words, the receiver did not hear what you said properly. He can tell something like, repeat that, I didn't follow, what did you say, so on and so forth. This is a negative feedback. So N stands for negative, negative acknowledgement. This is positive acknowledgement. Now, do we really need both? Now, you may be tempted to say that negative feedback alone will suffice. You don't really need positive feedback. In other words, if I'm not saying anything negative, assume that I'm receiving everything all right. Suppose your mother is nagging you about something you're supposed to do and you didn't do, and this is over phone, and you just keep the phone down and walk away. Now, does your mother have a way of knowing that whatever she's saying is actually getting into your head? No, right? So you have not really achieved reliability. What it translates to here is if the other system kind of crashes, then you think as a sender you're sending this packet, the other system has crashed, so it is not providing you any feedback. Thereby you're thinking that everything is all right, but in fact whatever you're sending is not being received by the other node. So we will address this issue of NAC versus ACK or NAC and ACK later in detail. But for now, let's assume that the feedback, the receiver feedback, is both in terms of ACK and NAC. So if the sender receives an ACK, he is going to send the next packet. So what should the sender do when he receives an ACK? That's right, he has to retransmit the previous packet. So the required functionality now so far boils down to this. We need error detection mechanisms. We also need a receiver feedback. For now, we are considering both ACK and NAC. Now, protocols based on this feedback and retransmission mechanism are called automatic repeat requests. They are called ARQ protocols. So here is our first version of reliable data transfer protocol in action. So you send a packet. When you receive an ACK, you send the next packet. On the other hand, if you send a packet and some bits are corrupted as represented by this, the receiver sends a NAC, and on receipt of the NAC, you resend the same packet because you realize that this packet is corrupted, so you're going to resend the same packet. So is this functionality adequate to provide reliability? What if the ACK or NAC got corrupted, in which case the sender has no idea on the feedback. It doesn't know whether the feedback is positive or negative. Now what should the sender do then? So if the designer is an optimist, he can just assume that the corrupted packet is an ACK and just send the next packet. But what if the previous packet was lost? Then your RDT protocol is not providing reliability. If you could also be a pessimist and assume that even though the previous packet is an ACK, it could have also been an ACK and thereby retransmit the previous packet. Now, what is the problem with this? If the previous packet is indeed not lost, now you are sending duplicate packets to the receiver. Our goal is to provide reliability, thereby this cannot happen. You need to assume the worst and send the previous packet. So now this retransmitting packet, previous packet, can potentially create duplicates. So how do you handle these duplicates at the receiver? In other words, what functionality do you need to overcome duplicates? Right, you need to now sequence the packets, the data packets that is. So here is a summary of RDT version 2. So the receiver provides feedback in the form of ACK and NAC. Now sender retransmits a sequenced packet on NAC or a garbled ACK or NAC. Now the receiver discards duplicates, if any, based on the sequence number because it remembers the previous sequence number, and if it sees the same sequence number again, it knows it's a duplicate, thereby it will discard it. So up till now, we saw that we need three mechanisms: error detection, receiver feedback, and data sequence numbers. Now that we are dealing with sequence numbers, an important question to ask here is what is the sequence number space? By what do I mean by this? Basically, the minimum number of sequence numbers you need to get the protocol in operation. In other words, do you need sequence numbers starting from 0 all the way till infinity? Or can you manage with just 0, 1, 2, 3? Or can you manage just with 0, 1 and so on and so forth? So how many sequence numbers do you need to make this protocol work? So just two sequence numbers, 0 and 1 will suffice. This basically means one bit which carries the value either 0 or 1 will suffice for RDT version 2. Why? At the receiver, suppose it has some packet, all it needs to know is whether the next packet is the same as this or the next packet is different from this. This distinction can happen based on just two sequence numbers. So here is RDT version 2 in action. So you sent a packet, it reached fine, ACK also reached fine, you move on to the next packet. In this case, you sent a packet, but it got corrupted. Thereby, you are sending a negative acknowledgement. Because of this, you are resending the packet. In this case, you send the packet, but the ACK got corrupted. So the sender now doesn't know whether the previous packet reached correctly or not. To be safe, you are going to retransmit the packet, but you are using the same sequence number as before. Since the receiver already received packet 0 before, it's going to view this as a duplicate and it is going to discard it. Now here is a case where the packet got corrupted, thereby the receiver generated a NAK, but the NAK also got corrupted, in which case you are again resending the previous packet. Now the receiver accepts it because it didn't get the previous packet correctly, I mean. So as far as channels with bit errors are concerned, are you convinced that RDT version 2 handles everything? In other words, there are no flaws as part of this particular protocol. Actually, it does. We have covered all possible combinations and handled it. But now I'm going to look at an optimization of this protocol. So I'm going to work with version 2.1. So what is this optimization? I don't want to use two types of packets, ACK and NAK at the receiver. I want to get rid of these NAKs. In other words, I want to go for a NAK-free operation. So the question here is, can you convey the same information as a NAK but through a NAK? How would you do it? So here is the answer. So instead of sending a NAK, what the receiver can do is it can send an ACK of the last correctly received packet. In this case, because it is ACKing some last correctly received packet, it needs to include the sequence number of packet being ACKed. Until now, the ACKs we have seen in other versions until 2 did not carry any sequence number, but here on they need to carry the sequence number of packets being ACKed. Now what does the sender do? Now if the sender sees a duplicate ACK, it can interpret it as a NAK and retransmit the current packet. So here it is in action. You sent packet 0, it received fine. You sent packet 1 and it got corrupted. So ideally earlier you would have generated a NAK, but what are you doing here is you are resending the ACK of the previous correctly received packet. Now it has already seen ACK 0 and it is again seeing ACK 0. This duplicate ACK is interpreted as a NAK and thereby you are going to retransmit the previous packet, which is packet 1. So dwell on it a bit and convince yourself completely that this indeed works. So in our optimized version, we need the error detection mechanism. We need receiver feedback, but now we are just relying on ACKs and we need data sequence numbers. But since we are relying just on ACKs, now the ACK carries sequence number of data packets. So far, we have considered a channel with just bit errors, and we started with just error detection and built upon it and added these 3 other functionalities. Now we will move on to channel with errors as well as losses. So how can losses happen at the data link layer? At times, the SNR is so low that you cannot even distinguish the signal from the noise. In other words, the noise dominates and thereby you cannot even recover any bit, in which case it results in a loss of packet. Also, a lot of implementations at the physical layer, when the physical layer detects that there is a corruption of packet, even though there are bit errors, at times it just drops the packet. It doesn't pass it to the data link layer. So that is an implementation artifact, but in general, you have to deal with both errors as well as losses as part of the RDT protocol. Now that we are considering a channel with errors as well as losses, do you think this RDT version 2.1 works? So consider these two cases. In this case, the packet got lost. In other words, it didn't even reach the receiver, and the receiver, for all it cares, it didn't see any packet, so it doesn't generate any feedback. In this case, the packet reached, but the ACK got lost. In other words, it didn't reach the sender. In either case, the sender gets no feedback. Until now, whatever we have seen, the trigger for a sender to act is based on feedback. Now, when it doesn't get a feedback, what do you need? You need some other mechanism, basically. So you need a timeout mechanism. The question next is, how long do you wait? In other words, when do you retransmit the packet? So timeout means you are timing out after some time and then you are going to retransmit the packet. The question here is how long to wait? What should be the value of your timeout? So how long to wait? This is basically a function of the link characteristic. In other words, you have to wait for as much time as it takes for the packet to reach the other end and for the ACK to get generated and come back. So this will be in function of the transmission time of the packet and the ACK, the propagation time, the processing time, so on and so forth. So this is something that is a variable that needs to be adjusted according to where you are using this RDT. So let's call this new protocol with timeout the RDT version 3. As you see the required functionality, now I have added a timeout timer. So here in this case, the sender waits a reasonable amount of time, which is a configurable parameter for the ACK, and it retransmits if no ACK is received in this time. Now there is a possibility that the ACK just got delayed and not really lost, in which case this retransmission is going to be a duplicate, but we already have a mechanism to handle it, that of using sequence numbers. So here is RDT version 3 in action. So by the way, this protocol we have described so far is also called stop and wait protocol. It is also called alternating bit protocol because you alternate between the sequence number 0 and 1. That is why it's called alternating bit. So when there are no losses, things are rather straightforward. You send packet 0, the acknowledgement acknowledges packet 0, you send packet 1, you get ACK1, so on and so forth. Now here is a case where the packet is lost. When the packet is lost, you are not going to receive any acknowledgement. Thereby you wait for some timeout, and then you are going to retransmit the packet. In response to this, you get an acknowledgement, and then again things go on as usual. So here is a case where acknowledgement is lost. Because acknowledgement is lost, the sender doesn't know the status of the packet. Thereby again it will time out and resend the packet. In this case, the packet happens to be a duplicate because the original packet itself reached the receiver. In this case, the receiver uses the sequence number to identify that this is a duplicate packet, and it is going to discard the packet. But in spite of this, it still sends an ACK. Why do you think it should do that? So that the sender knows that this retransmission was successful. Now here is a case of premature timeout where you send the packet, but this ACK got lot delayed. So this is a delayed ACK. So this is kind of delayed a lot. So you timed out before and you send the packet. In response to this, you're again sending an acknowledgement. So when the first acknowledgement came, you are sending the next packet. This is the usual process. But when the second acknowledgement for the same packet came, it's a duplicate ACK. In this case, you are going to ignore this ACK because your state has changed. By state change, I mean you have already transmitted packet 1. So this ACK for 0 does not make any sense. So you can ignore it. Just to emphasize, in RDT version 2.1 on duplicate ACK, you actually retransmitted the packet. But here you are ignoring it. There you retransmitted it because the state didn't change. Whereas here the state has changed. That is why. So as you can see, in some cases on receipt of the same duplicate ACK, you're sending packets. In some cases, you're not sending packets. So you have to be very careful on when to do what. So that is the details of the protocol. So here is another such case. If you receive a duplicate packet at the receiver, should you always send an ACK? So in this case, it is redundant, but in general, it's always a good practice to send an ACK because you have no idea what happened to the previous ACK. See here, the previous ACK got lost, in which case it makes sense to send. Here, the receiver does not know the status of the previous ACK. Thereby, it makes sense for it to always ACK a duplicate packet. So this shows you some of the subtleties involved in the design of the reliable data transfer protocols. So these protocols have to handle many challenges. They have to handle ACKs packets getting lost, they getting delayed. We didn't cover these because these are kind of rare in the link layer, but packets can get duplicated, they can get reordered, your timeout values may not be set correctly, and the receiver itself may not be capable of many things. In other words, the buffer space could be really small, its processing capabilities can be limited, and you have to design these protocols where the reliability has to work correctly, and also this particular protocol has to work efficiently. What do you mean by efficiently? I'll cover it shortly, but these are the design goals of RDT protocols. So TCP is another reliable protocol which we will cover at a later time, and this is even more complex than what we have covered so far. And to this day, even though I've studied TCP, there is something I realize about TCP which I didn't realize before. So these protocols are very subtle. So a lot of research goes on in them. So the debate of NAC versus ACK, I said I will address later, so here it is. So we saw earlier that we could eliminate NACs and just manage with ACKs. Earlier we saw that eliminating ACKs and just managing with NACs doesn't work if the end system crashes. There are other problems also with this. Can you think of any other issues? So the way the NACs work is they can conclude that packet loss has happened only on detecting holes. In other words, they received packet X and they received packet X plus 2. That means packet X plus 1 is lost. So that is how they detect holes. Now it is possible that some packets get sent and the next packet, this X plus 2 packet, gets sent after a really long time, after X, in which case if this packet X plus 1 were to be lost, you are not going to recover it, and that's not a good thing to do. And there is another fundamental problem. What if the last packet of the flow itself is lost? Now the receiver doesn't know that it is the last packet, so it's not going to generate NAC, and the sender is going to assume all is well because it did not receive any NAC. So it's kind of a deadlock situation here. The one good advantage of NAC is if errors are infrequent, the feedback that you're going to provide is going to be very less. In other words, you provide a feedback only when there is error. Now that we have designed this stop and wait protocol, our RTT version 3.0, let's see how well it performs in terms of throughput. So consider this case where you are trying to provide reliability between two nodes AB, and the link that is connecting them is a 10 Mbps link. It has a 10 millisecond propagation delay, and the packets that I am going to send on them are 1000 byte long. And assume that the ACK packet is too small that you can ignore its transmission time. Now what is the throughput I am going to achieve if I were to use this stop and wait protocol? So in stop and wait protocol, you transmit the packet. Now this packet has to go to the other end, then the ACK has to come. So basically you're sending one packet this much duration. So it's one packet every TX time plus round trip time. This round trip time is nothing but twice the propagation delay. So if you plug in the values here, so you're basically sending 8000 bits over, this is the transmission time plus twice the propagation delay. Everything I've converted it into seconds. So this, if you do the calculations, turns out to be 384.6 kbps. Now remember, the original link was a 10 Mbps link and all you managed to get was 384.6 kbps. So the utilization as such is only 3.8% of the link bandwidth. So it is extremely poor utilization. The same can be calculated this fashion also. So out of this whole time, the useful work that got done was just this much time. So the useful work is transmission time over transmission time plus RTT. For this entire RTT duration, the link was idle. So you wasted the resources. So this protocol is an extremely inefficient protocol. So if we are commending ourselves on a job well done in designing this RDT protocol, the performance shows that it's not a very good job. So we got the protocol correct, but we still did not achieve a very efficient protocol. So we need to better this protocol. So here is a summary of what we have learned in this video. So reliable data transfer protocols provide an abstraction of reliable channel to the higher layers. So they in turn tackle unreliability. Now we have incrementally determined the required functionalities needed as part of this protocol. So we first considered only bit errors and then we added losses on top of it. And we saw that we need many functionalities: error detection, we need receiver feedback, we need sequence numbers, so on and so forth. The current protocol, while works correctly, it is still inefficient. So in the future, we are going to build on this framework. In other words, we will use all these functionalities that we developed, but we are going to make the protocol more efficient. So that's in the next video.